have discussed about the first law of thermodynamics for a control mass system, and we will try to work out a few problems to illustrate that. So, the first problem is given here in the screen. A piston cylinder arrangement contains 1 kg of water as shown in the figure below. So, the piston is spring loaded and it initially rests on some stops. A pressure of 300 kilopascal will just float the piston, and a volume of 1.5 at a volume of 1.5 meter cube, a pressure of 500 kPa will balance the piston. The initial state of water is 100 kPa with a volume of 0.5 meter cube. Heat is now added until a pressure of 400 kPa is reached. Find the initial temperature, final volume, work done and heat transfer, and plot the PV diagram. So, as we have done for the previous problems, we will do it in the same way. We will sketch the setup in the board. There are stops here and you have water. You have M is equal to 1 kg, state 1, P1 is equal to 100 kilopascal, V1 is equal to 0.5 meter cube per kg, P float, that is the pressure at which the piston will start floating, is 300 kilopascal, and a hypothetical point say 2 prime is a point where you have pressure equal to 500 kilopascal and volume is equal to this. Okay. The final state is not this. The final state is 400 kilopascal pressure, not 500 kilopascal pressure. So, you have to find out the initial temperature, final volume, work done and heat transfer. So, before doing anything, we will just try to draw a PV diagram for the process. In this case, in the problem anyway it is asked, but even if it is not asked, it is a good practice wherever work done is involved, we will try to draw the PV diagram. So, state 1, so what is the substance? The substance is water. This is the system. So, from if you know what is P1 and what is V1 from table, from water table, property table, you can find out what is T1. So, this is 99.6 degree centigrade. So, we can plot the state point 1. Now, heat is transferred to the system. Once heat is transferred to the system, this will be energized, but still the piston will not start moving. It will start moving when the pressure gets built up from 100 kilopascal to 300 kilopascal. So, with heat transfer at constant volume, the pressure gets built up from 100 kilopascal to 300 kilopascal. So, that constant volume process say is up to this. So, this is P1 comma V1, this is P float comma V1. Then from 1A it will move in a quasi equilibrium process, but the resistance pressure will be linear with x because it is encountering a linear spring. So, the spring constant is not given, but an additional hypothetical point 2 prime is given, which will help you to construct the straight line along which pressure and volume will vary. That is the purpose of giving this data point. So, this is your state point 2 will lie somewhere in between these two on the straight line. So, where will the state point 2 lie? It will lie at a point where the pressure is 500. So, you see here this pressure is 300, this is 500, state point 2, the final pressure what is given? Final pressure is 400. So, state point 2, this is 300, this is 500, will be somewhere exactly at the middle where the pressure is 400. So, this is 2. So, the question is whether it is P2 comma what is this V2. Okay. So, the process ends here at 2 to 2 prime. This is a hypothetical thing, this is just to construct the diagram. So, you can write P2 minus P1A by P2 prime minus P1A is V2 minus V1A by V2 prime minus V1A, right. So, out of these let us see what are known and what are not known. So, you have V1A which is same as V1, this is known, V2 prime is known, V1A is known, here P2 is known, P1A is known, P2 prime is known and P1A is known. So, from here you can find out what is V2. Okay. So, P2 and V2 combination will identify the state point 2. So, P2 comma V2 will identify the state point 2. So, from the table of water, by using this pressure and volume combination, you can identify what is the state point 2. Once you have identified what is the state point 2, see thermodynamics, most of the problems essentially boils down to identification of the state points, because once you have identified the state points you can substitute the corresponding properties in the relevant laws, expression of the relevant laws of thermodynamics. So, in this case what is asked, let us see, find the work done and heat transfer. So, work done, one to 1a the work done is 0, 1 to 2, 1a to 2 is half into P1a plus P2 into V2 minus V1a. So, here because the mass is 1 kg, total volume and specific volume will be the same. Okay. So, if you now substitute these values, this is 175 kilojoule. Okay. Now, in addition what you need to calculate is what is the heat transfer. So, let us calculate the heat transfer here. First law for the system, the by system we mean the control mass system here. So, this is m into U2 minus U1 plus W12. So, m is 1 kg. How do you get U2 and U1? So, from the table, so this is the additional thing that you have to do when you are solving for the first law problem for the heat transfer. So, from table you get T1, similarly you also get U1. So, whatever table you are using, if you are getting U1 directly it is fine. In some tables enthalpy is given and not U. So, you find U1 is equal to H1 minus P1 V1. Okay. So, U1 can be found out. Similarly, from state 2 U2 can be found out. So, you can substitute U2 minus U1 here and this will be 2435 kilojoule.
Sir, I think we must iterate if the state point is in the two-phase region. How to use this?
So, here there is an important question that if what happens if the state point is in the two-phase region, right. So, if the state point is in the two-phase region, the first of all if the state point is in the two-phase region, for state point 2 how do you calculate the internal energy? So, how do you ascertain whether this is in the two-phase region or not? See, at this given pressure what is Vg and Vf? If this V2 is in between Vf and Vg, then it is in the two-phase region. Okay. So, if it is in the two-phase region, then you can find out what is the quality X by equating V2 is equal to 1 minus X into Vf plus X Vg. So, from that you can find out what is X. Once you find out what is X, then U2 will be very similar formula, 1 minus X into Uf plus X into Ug. So, if it is in the two-phase region, you can appropriately calculate the property. See, property calculation is not the focus of this chapter. The focus of this chapter is how you can apply the first law of thermodynamics to find out the heat transfer for a given process. That is the major objective of solving these problems. But I would like to say that using these problems, try to familiarize yourself more and more in identifying the state points from the property table. See, the problems that we are solving in the board are done in a little bit of abstract manner. That means exactly I am not focusing on where the state point is. I am just giving you the concept that if you know these two, you can identify the state point. Now how to identify that state point? We have earlier solved several problems on finding out how to identify state points. In fact, in the very beginning of like how to read thermodynamic tables, I worked out one problem with the sole objective of identifying the state points. So using that as a template problem, try to identify the state point properly, because if you cannot identify the state point properly, you cannot get these numerical answers, right. I mean the conceptual way of solving the problem, illustrating that is my job as a teacher, but your job as a student is to go through all the details. So all these details I also went through when I was a student. There is not enough time in the class, in the lecture, to actually let you go through the details of the tables and find out the data and substitute the data here. So here the problem solution outline is conceptual. From this conceptual to the detailing, please take this as a serious job, because if you cannot do that, just giving the concept will not allow you to get the proper answer in a thermodynamics problem, and that must be taken very seriously, because for a practical subject, you know, it is not just the concept of solving the problem that is important, but the very act of solving the problem, that is also equally important. So we will work out one more problem before we stop for this particular lecture. So the next problem is problem 3.2. So consider the system as shown in the figure below. Tank A has a volume of 100 liters and contains saturated vapor R134A at 30 degrees centigrade. There is a valve that connects tank A with cylinder B. When the valve is cracked open, R134A flows slowly into the cylinder B. The piston mass requires a pressure of 300 kilopascal in the cylinder B to raise the piston. The process ends when the pressure in the tank A has fallen to 300 kilopascal. During this process, heat is exchanged with the surroundings, so that R134A always remains at 30 degrees centigrade. Calculate the heat transfer for the process. This is a very interesting problem, and let me solve this problem and give you certain interesting insights about this problem. So there is a tank A, this is the direction of gravity. The system is R134A. Now first, can you tell me what is the control mass system here? The substance in tank A or the substance in tank in cylinder B? Which one of these? See, first you have to ascertain what is the system here. If you say it is in tank A, then I will put an argument that then it is not a control mass system, because when this valve is open, the mass is leaking from tank A to cylinder B. Therefore, the mass of A is not fixed. Similarly, if you say it is cylinder B, I will argue that that is also not correct, because the mass of the R134A in cylinder B is continuously changing. So, it is not individually A or individually B, it is A plus B. So, where the total mass remains conserved. So, then for this A plus B, our problem needs to be solved if we want to apply the first law for a control mass system. So, state 1, it contains saturated vapor at 30 degrees centigrade. So, V1 is Vg at 30 degree centigrade. What is the mass of this system A plus B? The volume of tank A initially, that is the V1 divided by mass. The volume of tank, the volume of R134 in tank A. Yes. This volume is 100 liter and this specific volume is Vg at 30 degrees centigrade, that you get from the table. So, this is what you get as the mass. So, this mass will be required for your calculations. So, this is state 1. State 2, so at state 1 what is, so you may also require internal energy. This is Ug at 30 degrees centigrade, because if you require to calculate heat transfer, you will require internal energy. State 2, what is P2? So, let me read the statement. The process ends when pressure in tank A has fallen to 300 kilopascal, and at the same time the piston mass requires 300 kilopascal to raise this. So, finally the equilibrium pressure is everywhere in the system, pressure is 300 kilopascal. So, P2 is same as P lift, this is 300 kilopascal. Until and unless the pressure here is same as the pressure here, mechanical equilibrium will not be achieved and the process will continue. So, process has to cease only when the system has come to an equilibrium state with the pressure everywhere as 300 kilopascal. And during the process heat is exchanged so that temperature remains 30 degrees centigrade. So, T2 is 30 degrees centigrade. So, using this you can identify what is state 2. If you can identify what is state 2 from the table, then from here you can find out what is V2 and what is U2. So, what is the work done? This is simply P lift. So, this is integral P dV. So, that because the pressure resistance pressure is same as this P lift. So, this is P lift into M into V2 minus V1. Okay. That is the change in volume, and the first law will give you what is the heat transfer. So, the total heat transfer is for this problem is 84.61 kilojoule. So, with this we conclude our discussions for this lecture, and we will continue with more problem solving in the next lecture. Thank you.